Hopefully everybody that's going to be here is here so you don't miss out on any of the initial parts of tonight's lecture. So as we were just talking, the exam is this Monday night coming up. It will go back as far as bus architecture and VHDL and FPGAs, that sort of thing, as well as anything having to do with the three SAPs, the 8085, which in terms of our world is basically just knowing that it's not exactly the same as the SAP3, because it has interrupts. We don't have to know anything about the interrupts, but we do need to know there's a distinct difference. And then anything about the 8088 that we might encounter tonight when we're looking at its instruction set. And actually, specifically tonight, we're not going to look at the whole instruction set. We're going to look at one or two instructions, and we're going to look at all the variations of those instructions, particularly with respect to how they affect different types of addressing modes. Next Wednesday, we will begin looking at the ATmega 328P chip, which is on your Arduino board, and make sure that night you have with you the Arduino board and the cable that goes with it. Prior to that, I might put a link for you to download some software to your desktop just because it's big and might take too long during class. So keep your eyes open for that after the exam. There might be a need for you to download some software in advance of the Wednesday night session. I posted the grades for the first exam. I'm sure some of you are happy, some of you are less happy, but it should be, I can't see what you see, but basically you should be seeing a number somewhere between 0 and 10, which represents your 10 points that you're going to have on the final grade that are applied because of the first exam. It should be fractional, meaning you might have a 9.3, you might have 7.8, and so those points all go together as, if you think of it, if you flunked everything else in the class, had 0 on it, at the end of the semester, that would be your grade. You'd have that many points. The most you could have would be 10%. Anybody have any questions about the grades other than why did I miss those questions? Okay. Now, if you do have questions about...
Oh, yeah. Sorry. Will we get access to like a whatchamacallit, like our tests like marked what we got wrong?
That's too difficult to do. And so what you'll get is a time with me if you need it. Most people won't need it. Those people that do and need to know exactly what question they missed and all that sort of stuff, you can schedule some time with me outside of regular class time, and we'll go over your response and the question on the test, at least the answer to the question on the test. I don't have the questions myself, so you have to bring the questions with you. What we will not be able to do is publish those, because I teach this in this class in 2 regular classes, plus there are several people who are taking it who can't attend regular school, and they're still working on taking the test. They haven't had it yet, and so I can't publish the test at least until they've had a chance to take the test, and certainly I can't publish any answers until everybody that's doing it or doing retakes or any of the 1,000 things that Mercer allows people to do if you ask permission to do it. So I can discuss it with you, but that's the best we can do. So if you need to do that, by email you can make arrangements with me for sometime during my office hours. Office hours are usually Thursday night after class. And since y'all have Wednesday, that's going to put it the next night after class when we do those. And you get about 5 to 10 minutes is all you can have because I've got a lot of students. But if you need to do that and you'd feel better doing that, whatever, you can make an appointment. Those of you that just know you missed a bunch of stuff because you left it blank, well, you did. And no magic answer jumped in those empty slots, and so you didn't get those points. A lot of people did a good job on this. Several people couldn't quite tell what you were doing. One person origami'd their exam. I got back a whole bunch of little clipped out questions. Some people put line returns for some reason in the middle of their answers, so they all had to be hand graded. And they may not be correct grades on Blackboard yet because of that. So any number of things could do it. What I am hoping you're seeing is a number from 0 to 10. If you're seeing other numbers or computed numbers or what your final grade would look like, all those sorts of things, you can ignore those for now because it doesn't know how to do the math to calculate that. So the only column that should be there is one for exam 1, and it should be a number from 0 to 10, a fractional number. Anybody see other things on when they look at their grades? Okay, well, I'll assume that you guys can figure that out. Okay, so let us talk a little bit about the 8088. But to get there, I'm going to talk a little bit about the history behind it. Now, the history is old. I mean, we go way back to build the systems on which we operate today, because modern systems actually are backward compatible almost all the way to the first computer we're going to be talking about here. But we're going to go way back to about 1971. And the processor we're going to talk about is something called the 4004. It was a, let me get my fingers on the keys here, 2000 transistor. Okay, that key is mislabeled. 2000 transistor, 4-bit data computer. So this is 4 bits. It was designed by Intel as a suggestion to a calculator, a Japanese calculator company. The company wanted Intel to make about 8 different proprietary chips in order to run the calculator. And Intel suggested to them that they replace some of those chips with a general purpose computer. And a general purpose computer is simply one like the computers we use today, which is not specialized to do any particular problem, but if you write programs, can do many different types of problems. And so through a series of acquisitions and various things, ultimately Intel built the 4004, and it's pretty much thought today to be the first microprocessor of the same sort that we're using in computers today. The architecture of it is not much different than those we saw in the SAP 1, 2, and 3. And while it follows those same plans, we go all the way back to 1971. Actually, way back, I think, to 1969 was when it was first proposed. And this architecture is really holding up well. It doesn't mean there's not other ones waiting out there to do it, but the idea of a state machine and being a general purpose computer has held up well. 4 bits, though, allowed us to do binary coded decimal and small problems like that, but really didn't get into the problems that we needed. So around about the next year, 1972, a processor called the 8008, which was an 8-bit computer, was introduced. Now, you can imagine where the name came from. They just doubled the 4004 because instead of it being a 4-bit computer, it was an 8-bit computer. But this kind of anchored in place Intel's trend of naming things starting them with an 8. And so the 8008 was very popular in lots of industrial business machines, but it also had kind of a crossover into the, at the time, hobby world. Now, hobby computers of the day weren't sophisticated like the ones you might go out and buy today. Basically, you would buy a bunch of pre-assembled parts, and then you'd have to turn it into the computer you wanted it to be. And the 8008 was a pretty good machine. It has a different architecture behind it than do modern computers, although it's still the same as the SAP 2, 3 family. But simply because being an 8-bit with just the same amount of addresses, 16 bits that you might have expected in something like the 8085, it didn't have some of the registers and things that we need in order to accomplish that in modern computers. Around about 1974, let me get on the keys here again. The processor and everything was upgraded to be more like what we know today. And a processor which was called the 8080 came into play. It had about 4,500 transistors. And it was an 8-bit computer, just like its godparent there, the 8008. And it was very successful. It wound up in a lot of business machines and hobby computers of the time, although the most modern hobby computers, the ones we think of like the Apple II and things like that, had not yet been introduced at this point. Now, round about 1975, there was a split from Intel, and a company called Zilog was formed by those employees that abandoned ship. And they built a very popular computer of the time called the Z80. You may have heard of that one. The Z80 actually wound up in some of the computers like the Radio Shack TRS-80 and computers like that that were popular back in the late 70s, and kind of built the family of the idea of being able to clone a particular architecture into a different organization. Now, Zilog didn't particularly have any permission from Intel to do this. It's just the employees that had designed the original 8080 and that instruction architecture branched out and created this new company because they were fed up with Intel, basically. And the Zilog computer was introduced. Now, it was not an Intel product, and it still exists today. You can still go out and buy a Z80 and design a computer around it. It had a few extra instructions that made it a little faster, the 8080, and it also ran at a slightly faster computer speed. Intel knew there was a market to be had, and in particular, they knew that the embedded market was out there. So around about 1976, they developed something called the 8085. This had about 6,500 transistors, and it is basically the same thing as the SAP3 architecture we've studied, except this guy has interrupts, which we'll learn when we do the AT Mega chip. We won't even do it on the 8088, but it has interrupts. We did not. So there's a subtle difference between us. So somebody asks you if the architectures are the same. Well, they're the same, but they're not. You know, strictly speaking, they're not the same. But we have the 8085, which is the same architecture other than that as the SAP3. So we have jumped in kind of in the middle of the stream here with Intel products. Now, about the same time they were developing, and in 1978 they introduced a chip called the 8086. The 86 didn't mean it was one better than the 85. As a matter of fact, the 5 here simply meant that this processor ran on 5 volts, where the ones before it ran on 9 or 12 or mixed power supplies. But by the time we got here, they knew the bulk of industry, and particularly TTL, which was quite popular at the time, ran on 5 volts. So they decided to switch their processors to being 5 volt able, and the 85 in particular was a 5 volt. The 86 can be run on 5 volts, but also has other variants as well. The 86 now anchors us into modern times by having a 16-bit data bus. And 16 bits is kind of the smallest that practical computers of today still use. If you go out and today you get the most fancy pants i-something computer, you know, the i9, i11, the i45, it is backwards compatible to this machine. Meaning that if I wrote a program on the 86, it should run on the newer machines because of the way they architected their registers, because it uses little endian, and because of lots of things like that, which make it very compatible. Now, this would have been the ideal computer for opening up the world to private people like you and me. But IBM at the time did not take that computer. Rather, around about 1979, they took a computer called the 8088, which is 16 bits, and it is the same architecture as the 86, but cheaper. It was cheaper primarily because the 16 data bits it have are multiplexed, meaning half of the data bits have pins, and the other half share the pins with the address bus. And the address bus on these two computers is a 20-bit address bus, meaning 2 to the 20th addresses can be addressed normally. just without any fancy business. IBM picked this, so the original IBM PC was an 8088 with 16-bit data and 20-bit addresses. They actually did not pick it until 1981. So that's actually, I guess I should move my IBM PC happened right about here. But my dates could be off by a year or two in any direction. Around about 1982, because they were popular, the 8088, it turned out to be a popular machine, Intel introduced something called the 8286 PC. It has 134,000 transistors. I won't write the number out. And it was called the PC AT, Advanced Technology, or whatever they had the acronym of the day for it at the time. And it turned out as well, particularly in business, to be an extremely popular machine and started to introduce us to the world of more modern computing. You might ask, where in the heck is the 186? Well, I can't find my keys again. And the answer is it exists. It was not popular, though, and wound up in a few calculators and things like that. It didn't ever really make it into the world of personal computers or in proper computing. Won't even talk about the architecture. It was backwards compatible from the 286 backwards to the 8088. Actually, specifically the 86, but the 88 is so close that it doesn't really matter. Round about 1985, the 8386 popped into view. And it had 275,000 transistors. And it's really a 32-bit machine, meaning the data is 32 bits by the time we get there. But that still means 16-bit and 8-bit data programs will run on them because it's backwards compatible all the way to the 8088 or the 8086. That's important to remember that. It also might have been, I think it actually was, the first one with a built-in floating point coprocessor. Up to that point, you had to buy a separate chip and have it installed if you wanted to have floating point support that wasn't in software. By the time we get to 1993, we see machines like the 16 megahertz Pentium machine coming on the scene. Actually, I think I left one out here. I did. In 1989, we had the 8486, and it has 1.2 million transistors. And it's the one with the built-in coprocessor. I thought that sounded a little odd. But then we get to the Pentium by the time we get to 93. And there's an interesting thing about the Pentium. The actual Pentium processor itself was destined to become the 8586. But round about that time, Intel discovered they couldn't patent, copy mark, or trademark the numbers. And so somebody else could easily go out and build something with the same number. So they had to come up with a crafty name. And the name they came up with, Pentium, like Pentagon or something, has 5 built into it. So it was a 5th generation computer after the 8088. The Pentium was interesting, though. It really was not a very interesting computer internally. What it was a pair of 2 8486s sitting side by side inside the same chip. And one of the 8486s had been dumbed down. Basically what they did, they made one of them only able to execute certain instructions, but it was always safe to execute those in parallel with the other 486. So it gave you a huge speed advantage while using technology they'd already developed. Another thing that happened along about the same time as the Pentium is they had a couple firmware errors occur. One was big, significant one, had to do with floating point operation, and they actually had to recall a bunch of chips. The other one was a little more interesting because they actually counted or encountered the problem when they were testing the chips. Normally, you build a huge wafer of lots of processors, and then you cut them apart, and you test them, to make sure they really meet all the specs. And in that, there's a huge number of them that don't meet spec, and they get thrown out. Well, it turned out there was kind of an intermediate bunch of them. They could pass all the tests except for a handful of them. And what they did with those is the marketing people decided, well, we can sell those. We don't have to throw those away. And what they did is they rebranded those chips. And they're really just simply the same Pentium chips. They just had errors on them, so they couldn't sell them as Pentiums. They called them Celerons. So the old Celeron process, although it's lost its stigma, originally was the broken Pentiums. Modern times you can buy a Celeron, and it's a slower version of the same Pentium chip, but it's not put there because of the errors. It's put there because it was designed to be slower and cheaper. And then the last one I have on my list here is around about 1995. We're still before the year 2000. They came out with one called the Pentium Pro, and it's bigger, better, faster, and so forth. As we move forward in time, we get to whatever the most modern chip is of today, and that seems to change weekly. But whatever it is, we're able to say that that chip is more than likely, if it's able to run Windows 10, it's more than likely able to run all the way back to programs we would have written on the 8088, which is really the 8086. And so I think knowing a little bit about the architecture won't hurt us. And as a matter of fact, it'll be quite useful to know as you go forward in your skill set. We're not going to learn the assembly language for it because, number one, it could take an entire semester to learn because it has a lot of sophisticated instructions. And secondly, if you ever have to write in IBM assembly, just like we did with, I said, Verilog back when we were studying VHDL and Verilog, you're going to learn it on the job. This is a language you're not going to use daily, but when you do need it, you're going to have to be able to remember the architecture more than the individual instructions. Whereas the AT Mega, when we learn the assembler for that, that has practical, I can call them hobby uses, which could lead to things that you would need to do in a job where it's more likely to be necessary to read assembly code than it is on the PC. Since most of the high-level languages on the PC have become very smart, very sophisticated, and actually in general can write better assembly than a human can. So when they generate the assembly code that comes out, it's generally better than a human could do. And it's only necessary for us to go in and write assembly if it doesn't get it right. Very rarely do we have to do it to make it faster. That's a kind of a something people make up to sound like a reason why they think it's cool to write assembly. That's not a reason. The reason is because sometimes the compiler actually generates bad code. And while it can generate very sophisticated code, when you turn on full optimizations in a compiler and it's throwing away instructions and doing all sorts of very heavy-duty optimizations, it can actually wind up occasionally with code that doesn't quite do what you ask it to do. And that's when knowing the assembly comes in the handiest, in that debug phase. Okay, so let's look at the programming model. Hopefully you downloaded that before class. If you didn't, I think I already deleted the URL for it. But if you haven't done it, let's put it back up there so you can see what it was. Oops, I hit the wrong button. So if you haven't downloaded it, you want to download from that URL right there. So this is the architecture. I'm going to bring it up in something I can write on, so I'm going to minimize it for the moment. And hopefully I have a copy of it. I do. Put that there so you can see it still. Okay, so this is the programming model, very similar to what we had talked about with the SAP 3's model in that we don't have a lot of detail here, But once we had learned the instruction set, we should be able to use this model to know how to write those instructions. We'll know what the parameters to the instructions actually can be. Now let's take a look at the model in general, and then we'll go do some specific things with it. First of all, there are 8 registers, which are your main registers. The A, the B, the C, and the D. But the names of them are not A, A, F, B, C, D, E, that sort of name. Instead, it's AH and AL. Both of those are 8-bit registers, which can be taken together to be a 16-bit register. And when they are, you use the name AX to refer to that set of 16 bits. So the AX register consists of AH on the left and AL on the right. Each of these are 8 bits wide. But if you refer to it as AX, it's a 16-bit wide register. Anybody have any question about that? Because it's profoundly important to the remainder of the discussion. Okay, think of AX, just like you did in the last computer, of referring to the same 2 registers as the individual names. So if I change AX in any way, I'm actually changing AH and AL. If I change AH, I'm changing AX. I change AL, I'm changing AX. But if I change AH, I'm not changing AL. Those are separate registers. It's only when they're pulled together under the name of AX that they become a 16-bit entity. BX is the same way. There's a BH register and a BL register sitting underneath them. If we're working with 8 bits of data, we could use the 8-bit version. If we pick the 16-bit, we would use the BX version. So we have AX, BX, CX, and DX. Now in the instruction set, kind of a mnemonic to remember these by, A stands for accumulator. So frequently, this is used as an accumulator, either as AX or as AL if you're using it as a 8-bit register. AH is used for things, but AL is specifically the one thought of as the accumulator when you're working with 8-bit arithmetic. B stands for base, B-A-S-E. And what it means is this register is often used to contain part of an address. And it's the address portion from which we can base offsets. And just think of it that way, and we'll get more detail about that in a few minutes. But we can base offsets that we're going to present on a particular place, and we can set that place in here, which becomes then the base of those offsets. C you can think of as the word count. C is often used in some of the instructions to hold a number which is counted down or counted up. Like you think about a for loop in high-level language where you have I equals 0 and you count up, incrementing each time. The C register might often be used for something like that. Either CH or CL or CX itself as a complete register of 16 bits. The D and the DH and DL register stand for data. And this is often used when we want to store pieces of data. We use this register. Now we can use any of them to store data, but if this was being used as an accumulator, this was being used as a base, and this is a counter, we need some place to store data. Well, here it is. We could use the D register. 16 bits would be stored in DX, and they're really DH and DL pressed together, but if I only had 8 bits, I could store it either in DH or DL. Everybody see that? Now, if you have a question, this would be a good time to do that, to talk about it. Okay, now we have 4 registers which are only 16-bit long. These are all 16-bitters. First one is called the stack pointer. The second one is called the base pointer. Base means the same thing, but it means I can have two different types of bases, one here and one there. But the B again stands for base, and it's base pointer. Now we have two registers, which are 16-bit general purpose registers for using, but there's a set of instructions which are called string instructions in the 8088. And string instructions allow you to operate on a series of bytes in a row, terminated with a 0, and when you're working on them, you might be moving them from one place to another. Maybe you're going to move a string from some place to another place. The S in this stands for the source index. The word source, S-O-U-R-C-E. The D in this stands for destination index. These also are commonly used because of the I part of their name. Again, a mnemonic for that is this is index. So both of these can be thought of as index registers for instructions that are not string related. So those are both index registers. If I needed to index into an array, and I need the index, I could use one of these to hold that value. Notice up here when I talked about this being a stack pointer or a base pointer, these are also called pointers. They're able to hold indirect addresses, meaning the address can be inside of either the pointer here or the pointer there, but usually we're not interested in the value within them, we're interested in where they point. So that's some more detail about this block of registers here. Okay, Nicholas, tell me about the AX register.
The AX register, it consists of the AH and AL registers, and they are used as an accumulator, mainly the AL one.
Okay, how big is the AX register?
The AX register is 16 bits.
Okay, how big is the AL register?
8 bits.
Okay, so 8 bits is a byte, 16 bits is a word. Anywhere we're going to see a number written as a word, meaning a 16-bit number, except when it's in memory, it'll be in the right order. The high will be on the left side of the low. In memory, though, if we look at memory, just like the SAP3, it's going to be in Little Endian, and the SAP2 for that matter. And because of that, we would see, if we stored the AX register in memory, we'd actually see the AL byte in front of the AH byte in memory. Anywhere else, it'll show in the correct order. Okay, so we didn't talk about these do yet, but we'll talk about them when we're going to be talking about our addressing modes. Just be alert to the fact that these are both pointers. They can point somewhere. And these are both indexes. They can index somewhere. In my head, that says, I wonder if they could index somewhere relative to a pointer. Or could they index somewhere relative to a base? We have two things that say base. That makes me interested in this instruction set even more. We have a flags register. The flags register on this machine is 16 bits wide. We're not going to talk about any of the particular flags that are in it. There's just a few more than we had, and not all 16 are used. Just like on the SAP3, we didn't use all the flags, but we had positions so that it could have easily grown to 8 of them. But the sign flag, the carry flag, the parity flag, and there's other flags inside that flag register, but we should be aware that it's there. Now, we don't call it a program counter on this machine. Don't fall for that on the exam. It's called the instruction pointer. These, again, are all 16 bits wide. And it's the equivalent of the program counter, meaning it generally, you know, depending on how far through the instruction you are, but it'll point at the next byte of data to be retrieved for the next instruction. So we want to just be aware that the name changed. Now you might be looking at this and, you know, if you're a crafty thinking person, going, wait. I'll write wait out so that I can make it look like I knew what I was doing here. Wait. Okay, who wants to tell me what question I'm getting ready to raise? Had somebody in the other class tell me. Okay, let me go back and repeat something about this machine I said earlier. This has 16 bits of data and 20-bit addresses, and it is backwards compatible all the way to the 8088 itself, because it is an 8088, right? So anything written for the 8088 or 8086 will run on these machines. It's just going to run slower on an 8088 because we can't use the address bus to show all 20 lines. We can only show half of those because 8 of those data bits will be taken up by data half of the time. So what question we're going to get ready to raise based on what I just reviewed with you?
How do you address the 20 bits with a 16-bit pointer?
You got it. I got 16 bits. We have 20-bit addresses. This seems to be a bit of a problem, doesn't it? Seems like we're going to run into a little issue here. So let me show you how they solved the problem. And this is solved similarly today, although they use lookup tables and things today to make it easier. But down in the core of the machine, they still have the same thing going on. Okay. Where in the world in this machine can I store addresses? Well, I can store them as constants. I'm going to write them in big Indian format here. So that's a constant literal of 1, 2, 3, 4. I could also store them in the B register because the B register is a base register. So let's just put 5, 6, 7, 8 in there. Now if I were to ask you what value is in the BH register, you'd say 5, 6. If I ask you what's in BL, you'd say 7, 8. If we saw this in memory though, we'd have to remember that the 7, 8 would appear before the 5, 6, just as in this case the 3, 4 would be before the 1, 2. The stack pointer and the base pointer can also contain addresses, but they're all 16 bits. So if we solve it for this, we can solve it for all of them. Brings us to these 4 registers right here. These registers are what are called segment registers. S-E-G-M-E-N-T. And here's the way they solve the problem. They take a segment register. Let's say we're going to take it doesn't matter, a segment register. And let's say it contains the value 2000. That's in the segment register. Now we've been told that this address is with respect to that segment. So the way we compute the actual 20 bits is we take what's in the segment register. We add one more 0 on the end of it. We basically shifted it left 4 positions. Then we add 1, 2, 3, 4 to it. So this address, if we knew we were working with respect to a particular segment address, would get computed as 2, 1, 2, 3, 4. And that's where the data that's referred to by that address lives. Obviously, we'd have to know which segment we're currently using so that we could make that addition occur. And of course, if these values had numbers in them, they would add to this, and it wouldn't look like 1, 2, 3, 4 at all when we were done. Now, one of the things we'll learn later is every physical address in the machine has 16 different addresses because it's in a different segment 16 times, at least in terms of the fact that we had to shift this to the left by 16 in order to get to a spot where that byte could be added in. So every segment begins on something called a paragraph boundary. I'm just going to write P-A-R-A because I don't want to write out paragraph. And a paragraph is like a byte and a word and a double word. A paragraph consists of 16 bits on this machine. So a nibble is 4 bits, a byte is 8 bits, a word is 16 bits, and then a paragraph is additionally going to be 16 bits. But we normally speak of a paragraph in terms of addresses, whereas a word is thought of in terms of using it as data. Now, what are these segment registers and when would we use them? DS stands for the data segment. Usually, if we refer to a piece of data in memory, it's with respect to the data segment. So if we'd been told this was the address of some data, we would go to the data segment register and add it to this after it had been shifted left by 4 bits. The SS, or the stack segment register, is used with respect to where the stack pointer is pointing or where the base pointer is pointing. So unless we do something to make them not point there, the stack pointer and the base pointer always point to a spot that's inside the stack segment. Now the code segment register, the CS, is used with respect to the instruction pointer. So wherever the code segment puts us, you add the instruction pointer to that, and that's going to be where the instruction we're executing currently lives. So let's say the code segment contained 1010, and we'll say the instruction pointer was 0002. We'd add a 0 to the code segment. We'd add 0002. We'd add them up. That's 10102. And that's the physical 20-bit address that we have the next instruction sitting at. Then finally, we have this bad boy up here called the extra segment. Then you did an extra one in case you need it for something. So it's an extra free, it's a free player. You can use it for whatever you want, but you have to tell instructions that you're using it. The string instructions use it. So sometimes you're moving the string from one place to the other. It'll use the extra segment for one of the operands and the data segment for the other one. We're not doing the string instruction, so we don't have to worry about that. So this just becomes one that if we wanted to, we could have an extra place where we've reserved some memory for special values. And when we wanted to get to them, we'd have to use them with respect to the extra segment. I've seen some security code, it's pretty bad security code, but I've seen some that uses the extra segment to prevent people from easily finding your password, which they're storing in the clear for some reason. So this is important, very important. The addresses are 20 bits, and they're only given to us by virtue of the fact that we combine a segment and an address portion. We call this portion the EA. Yeah, I know all of you ran to get your Madden games out or something. But this stands for the effective address. So the effective address is 1234. The real memory address is the segment plus the effective address. And if we were computing t-states, computing different EAs cost different amounts of values. And we're not going to go through the details of that too much, but just be aware that some of them are going to be cheap to do, and some of the effective addresses we're going to generate are going to be hard to generate. This address we got, these 4 digits, might be just hard-coded in memory, or they might be computed and then used in an instruction with respect to a particular segment. And that won't make much sense until we actually look at an instruction. Okay, anybody have any questions about anything that I've scribbled on this page? Zachary, you have any questions?
No, I do not.
Okay. How about you, Kyle?
Not at the moment.
Okay. How about you, William?
I'm good.
Okay. So we want to remember this model. We won't pull it up too many times, but just remember what it looks like. Hopefully you printed yourself out a little sidebar copy there to have. And we're going to look now a little bit at how we would use some of this stuff inside of an instruction. So let me actually, I can just use this guy, I guess. Whoops. Well, I'm going to focus for the moment on the move instruction, although I may throw a few more in as we're going along. I'm going to indent them because they would be indented normally if they didn't have a label. And I'm going to tell you that the opcodes are different than they are in the SAP3 and the 8085. That's why we're not really backwards compatible with those machines, although those machines are backwards compatible with the 8080 and a little bit compatible with the 8008. And it was the trafficking through there that it turned out to be that Little Indian came into favor. The reason was a lot of those machines, you could give them a 16-bit program and they would still work because they were using only the lower part, which came first when they pointed at a particular address. And because those machines didn't have enough memory to need the other part, there always were zeros in the high part anyway. So when you would move one backwards in time, that kind of generated the requirement that Little Indian, at least, or at least the fact that Little Indian seemed to solve a lot of problems. Turns out later it also solves some other internal problems, but we're not going to get that technical about it. So let's just write a bare bones move instruction. Let me get my fingers close to the keyboard here. Do I want to write everything in uppercase? I guess I do. What would you think that instruction would do? Who wants to tell me? Somebody pop your microphone on there and tell me.
Would it copy the data from AL and move it to AH?
That's right. It takes the data that's in AL right now, and at the end of that instruction, AH has the same data in it. Okay, notice that it is moving 8 bits of data around. And it's moving from one register to another register. Oops, I forgot I had that locked on. What do you think that one does?
It moves from the 2 registers compromising BX to the 2 compromising AX. Right,
and we can just think of instead of even worrying about AH and AL, in this case, we just think about we're moving that whole 16 bits to the other 16 bits. We're copying. When I say move, I mean copy, of course. Now, these are both move instructions that move from a register to another register. And I'm going to write over here to the side. This is called register mode, or the addressing mode. Both of those are. One is 8-bit to 8-bit. The other is 16-bit to 16-bit. What does that one do? Who wants to tell me what that instruction does?
It might replace DH, or it might copy DH into AH.
Good yes, but no.
It doesn't do anything?
Well, it's probably going to do something.
Maybe it copies DH into AL.
Well, all of those are good guesses. And not knowing more, what's the old thing? It's a sick bird. What is sick bird? Illegal. Okay? So we got a sick bird here. That statement will not make it through the compiler. It can't be encoded. So when we sit down and we try to write that instruction out, we're going to find that one cannot be encoded. We can't move 8 bits into 16 bits or 16 bits into 8, which that makes a lot of sense. But all your proposals there were good ones. Perhaps it, under the hood, says, well, DH should go to AL because it's the accumulator or something. But no, it's actually an illegal statement. So we're going to take it off our list, and if we're asked to ever encode one of those, we're going to get in trouble trying to encode it because we're not going to be able to. We'll get stuck trying to encode it. Now, register to register is a form of instruction which is going to be fairly common. I mean, we saw in our other machine, we had lots of uses of moving things around. And so storing things in different places, tucking them away somewhere, is very often used with this. One of the things we're going to find when we get ready to encode these instructions is that there actually is 2 separate opcodes for the, well, I shouldn't say opcodes. 2 separate instructions will do exactly this. 2 instructions will do exactly that. And you might go, well, that seems a little odd. And yes, it is, but it's an artifact of the way they do their instructions. There's a certain symmetry that causes this to be encoded in 2 separate ways. So you want to watch for that. If you were to give a test or something during the next couple of weeks, you want to make sure nobody had given you the alternate form trying to trick you into thinking it was the original form. So when we start encoding things, pay a lot of attention to the fact that some instructions might have multiple encodings. And in particular, it's the register to register ones. But in all cases, the number of bits we transfer has to be equivalent. So 16 to 16 or 8 to 8. Now, in general, we can't specify any of the special purpose registers here. There are some special instructions, and again, they would be moves, which can use to be moving, for instance, one of the pieces of data into a segment register, because obviously you have to load them with something. So to load a segment register, we actually use a different version of the move instruction. We'll talk about that later. But we wouldn't expect ever to see a segment register name here. We'd also, in this, never expect to see one of the 16 bits. So I'd never see stack pointer here because it's not 8 bits. I might see stack pointer down here because it could be moved into the base pointer, for example, or into AX. So 16 can go to 16, 8 can go to 8, but nothing on the left-hand side can be tampered with these instructions. So none of the base registers or the instruction pointer can be touched. And you also can't use the flags register because it doesn't really have a name. I called it flags in the handout, but it doesn't have a specific name like that. Okay, so let's look at another thing we might encounter along the way. Oops. What do you think that instruction does?
Does it move 1, 2, 3, 4 to CX?
It does. It does exactly that. In the instruction, when we look at it, we're going to see the coding for CX, a coding for the move, and a coding for the 1, 2, 3, 4. So this is hardwired into the instructions. We already know the name of this addressing mode. It's called immediate. So that's using immediate. Or sometimes we use the word direct. But for the purposes of what we're going to be using in our talking about it here, hang on a second, I have to move something that's getting ready to fall off my desk. in this particular instruction. I'm going to leave the name immediate because we may see it in a different way later. How about that one? Do you think that's doable?
It's illegal.
This one is not illegal. This one's actually legal. What gets loaded into DX, do you think?
00 FE.
Good guess, but no.
FE?
What'd you say?
FE?
Well, that's only 8 bytes or 8 bits. We need 16 bits. What are the other bits going to be?
0, 0, or
Well,
all zeros.
Yeah, unfortunately not. For our purposes, actually, it is fortunate that it's not. But what we look at the left bit of this, is it turned on? Yes, it is. So if it's turned on, the register is loaded with FFFE. If this had the left bit turned off, for example, 7A, it would have been 007A. It propagates the left bit of that nibble into the sign portion, so the piece that's there. So anytime we have 8 bits going into 16, the number that you have here will be sign extended, and the sign is look at the leftmost bit of the 8. If it's turned on, we have all 1s in the other positions. If it's turned off, we have all 0s in the other position. Is that going to be legal?
Yeah, should be.
Yep, and what's it going to move into DH?
Just FE.
Exactly. That's exactly right. Oops.
I'm guessing that's illegal.
How much are you guessing by? Or would you give me a point off your test grade?
No.
Oh, okay.
Whether it's legal.
Depends on the assembler. Normally this is illegal because it has 16 bits. Even though these are zeros, it doesn't know it can get rid of them. So we would consider that to be bad coding practice at best. But good answer. Your answer was good. Okay, so these actually have an addressing mode. If we think about what type of thing they are, they're not register. They basically are an immediate mode instruction. And so that would be another way we can address data. In this case, the data we're moving is in this register and is moved to another register. So it's a register type of addressing. In this case, this guy is immediately available. It's in the instruction. It's immediately available. It's immediately available. It's right in the instruction. So let's look at something similar to what we saw in the SAP3. Let's use a different register here. What do you think that instruction does?
Moves the contents of the memory into BX.
Right. It goes to 1, 2, 3, 4. Now think about what I'm saying here. It goes to that address, but it goes to that address relative to the data segment. So we have to know what the data segment has to compute the whole address. But the effective address is 1, 2, 3, 4 in the data segment. Every segment can only be 64K, obviously, because this could be biggest FFFF. When it gets to this address, it's going to find 16 bits of data. It needs 16 to fill this register, right? The stuff it finds in memory is arranged in little Indian form. So it's going to get the low byte first, put it in BL, then get the high byte and put it in BH, and when you're done, BX will contain the right value. So this address is going to be used to find 16 bits of data in memory, put them into BX. And because it's just a plain old move instruction, we're moving into BX, then we're going to be relative to the data segment. Okay, now, is that legal?
Yes.
Absolutely. Because the data we're going to get in this case is only 8 bits, but the address is still 20 bits, right? 16 in the effective address, 4 left over from the segment. Again, data segment, and we're going to go to address 1234, find the 8 bits that are there, and put them into BH. This is some sort of offset addressing, but in our world, even though we called the last one for 2 seconds direct, this is actually what's called direct addressing. We're directly going to this place, picking up some data and moving it into the registers. Now we have to be a little careful here because it is absolutely legal. It's going to be sign extended to contain zeros. So the actual address is 0034. We're going to go there, get 1 byte. What segment are we relative to?
The data segment.
The data segment, the DS register, that's right. Now, direct addressing is very useful, and we want to always keep in mind that the size of the address and the data place we're putting it really aren't related. So if I say, move to AX, whatever is at 1.2, that's completely legal, and that's called a direct address. Now, in the other world, when we were using it on the SAP2, we called it an indirect address. So this is really kind of an indirect address, and this is more of a direct address. But the Intel used the words immediate for this, and they used the word direct for this. So we'll stick with it till I change it a little bit later on some other things. But that's another form of the move instruction that we have available to us, which for data sometimes is useful. This stuff is typically constant, right? We knew it when we assembled the program. This location is known at assembly time, but the data that's in it isn't known. So we'll load that memory right to the memory, change the memory. This also means that I can put it on the other side of the thing. I can move to address 1234 whatever's in the AL register. And it's at a direct address. And that address goes into memory in the data segment at offset 1234 in the data segment, and we put 1 byte, 1 8-bit entity at that location. Had this been like this, we would have put 2 bytes there. We'd have put the low byte first, then the high byte. And it's not this low byte and high byte, it's whatever's in AX. So the low byte of AX gets put first at 1234, then the high byte gets put at 1235 relative to the data segment. Everybody feeling pretty good about these? Any questions about either register, immediate, or direct addressing?
So is there no dedicated move immediate like MVI instruction for the 8088?
Not in that same form. That's correct.
Okay.
Because if you think about it, basically that's what this is doing.
Yeah.
Okay, so let's assume we wanted to get a little fancier than this. Let's say that I knew this address, but I really didn't know it well enough to put it into the instruction. Rather, I put this ahead of time into some register somewhere, like I'm moving it into BX. Well, BX contains a register I'm interested in. So I should be able to say something like move, let's put it in AX, based on the address that's contained inside of the BX register. The BX register, remember I said that was called a base register? This addressing mode is going to be called base relative. So that instruction says, go to the place in memory, and specifically in the data segment, that's offset by BX, whatever's contained in BX. Pick up the 2 bytes that are there, put the low byte in AL, put the high byte in AH, and when you're done, AX will have the value this pointed to. Everybody pretty happy about that one? What does that one do?
Does that you said receives the data from the BH register and moves it to BAH?
Well, inside the brackets, since we're doing base relative, this thing has to be a pointer to some memory location. All pointers are 16 bits long, so this is an illegal instruction. The only 2 base registers that can ever appear in these instructions are BX or BP. Now, BP has one other little twist going along with it. It is not relative to the data segment. It's relative to the stack segment. So in order to compute the address for BP, we need to use the stack and not the data segment register. This addressing mode has a slightly different name, called base relative stack. So let's assume for a second here. Currently the AH register contains 4444. This is what AX contains. The base register, BX, contains 1234. The BP register contains 0003. Data segment contains 1000. Stack segment contains 2200. What value is going to be in AX after that instruction is executed? Saw a question just like that the other day. Okay, what's the effective address of this portion of the instruction? Well, it's whatever value is inside BX. So to get the real address of that operand, we need to take the data segment, which is 1000. I'll move all my keys one position over and add a 0 on the end of it. And then add to it the BX register. So 11 is the place we're going to go to, and when we get there, we're going to pick up, because this is 16 bits, we're going to pick up 16 bits of data. Now let's assume that at that address, we have 7833. So it's going to pick up the 78. It's going to put it in the low part of the register. It's going to pick up the 33 and put it in the high part of the register. So when that instruction's done, AX will no longer contain 4444, it'll contain 3378. The advantage of this instruction is we don't have to know this number at compile time or assembly time. It can just be in a register because we've computed it, and then we can just use it. Very powerful stuff. Very high-level language supportive. Let's do the second instruction there. BP contains I can get the 30K. The stack pointer, or is relative to the stack segment, is this guy here. So 20 0, we add those two guys up. That's the address in memory of our data. Let's assume when we get there, we have a 4534. We go there, we see we only need to get the first 8 bits. So we're going to go get the 8 bits, which is a 45. Put them in AH, which means they'll overwrite the 33. Now the AX register contains 4578. Did everybody manage to work their way through that with me?
Could you explain one more time why it only grabs 2 of the digits?
Because the register we're putting it in is only 8 bits wide.
Thank you.
Okay, well, let me get rid of that. Junior Watson and little Tommy Tuttle one day were out working on a program, and they noticed that they knew the starting address, but the data they wanted wasn't in the first byte. They said. And they asked Intel if they had an instruction which could do the following. Intel, of course, came back and said, whatever you wish, sir, we have that. Name of this particular addressing mode is called base relative direct. What it says to do is take the address offset, the starting address point, add to it 2233. This is done at assembly time, kinda. I mean, the addition actually happens at runtime, but if turn this from a word into a number would happen visually. Once you've done that, these two values are going to generate a particular number, which is the effective address. Take that effective address and add it to the data segment address, which has been shifted left 4 bits. Go to the spot you just calculated. Pick up the 2 bytes that are going to go into BX and put them in BX. Just don't forget they're in Little Indian in memory. Do you see how practical that might be? Imagine in your program you had a table. I'm going to just write some arbitrary, define a byte here. And you had in your table, here's a byte of zeros, here's a byte of ones, I don't know, maybe even some up here at the original place. And down here, this is the secret numbers down here. And the secret number is a 33. Well, wouldn't it be nice if I could just simply say, give me that byte directly? and I don't even need to use that word. I just know that's where it is. That could almost be a comment. Well, the way I would do that is I would put the address of table in the BX register. I would then add to it an offset or a direct offset of 1, 2, 3 of 3. So it would be where table starts plus 3. Give me that byte, or in this case 2 bytes. So I probably should make these words, I'll make this the BH register so it matches the data. So that's a use of base relative direct. Very powerful. And that we can anchor down a data structure and we can index into it if we know the indexes, and we do if they're used by name at runtime, as opposed to something like an array which is variable at runtime. This byte is never going to move relative to where table begins. It's always 3 bytes further. Everybody see that? Now let's go CH. Who wants to tell me about that instruction? Somebody give me a green light and I'll call on you. Gotta get those participation points. Okay, go ahead. Basantia. Basanthi, do you have the answer? What, you got a green light? Let's go down here. William, tell me about it.
Well, we know the base pointer is going to have a value in it. We're going to then go 13 relative to it. So that will actually give us the effective address, and then we'll take the data from that effective address plus the stack segment to find the real value.
Right, it'll be in the stack segment. Yeah, the pointers are in the segment. So you think of the segment as being the higher order thing. We actually write that. If we're writing it out, we'll say things like stack segment relative base pointer inside of it. So you can actually write down the number. That's what's in the stack segment. That's what's in the base pointer. But sometimes we notate it like that. I don't think in this class we'll need to, but that's just something that you may benefit from later. So what do you think the name of this thing is, William? The addressing mode.
Base pointer relative direct.
Well, we're building a trend here, if you notice. Okay, base relative direct stack.
Stack.
Just put the word stack on the end of it if you're using the stack segment. Okay, now, let's say I had this instruction, but I didn't want it to operate in the stack. I wanted it to operate in the extra segment. I'll repeat that line again so I don't have to type it. Oops. Man. All I have to do is I prefix the brackets with the name of the segment that's to override it. So that instruction now says, and it's still base relative direct stack because of the fact we're using this addressing mode. We would also add the words overridden to the extra stack, but I'm not going to type all that out. And so what that says here is take the value in the base pointer, add a 13 to it. Once you've done that, I'm considering these hex digits right now. Normally they'd be decimal, but we're considering them hex. So add 13 hex to the base pointer. Take this, add it to the extra segment, which has been shifted left 4 bits. Go there, get 1 byte of data, put it into the CH register. but it has exactly the same thing. So this could be overridden to be the extra segment, or from the stack, it's sometimes overridden to be the data segment. Very rare to override to the stack segment or to the code segment. That would be very unusual. So extra segment and data segment physically are what would go there. Okay, I'm going to get rid of that instruction because it could be confusing to somebody looking at it, like me. Now we think, that's plenty of addressing modes. But Intel said, no, it's not. You guys actually do some other stuff that you're just not thinking about right now. And we do? Yeah, as a matter of fact, one of the things you do is use arrays. And when you use arrays, generally you use a register to contain the index of the particular value. Yeah, I guess we do. So are you telling me that I can write an instruction like this? Or I could write something like use those index registers we had? And they go, yep, you can do that. What that says is go to the contents of the index register, get a byte of data, or 2 bytes of data in the first one, and put it in the AX register. Go to wherever the DI register points, get the byte that's there, put it in the BH register. Very similar to the base relative, except these are indexed. So the mode for these are called indexed. Both of them. There is no stack variation of indexed. Well, at least not yet. And you say you kind of like that. Well, of course you do. You don't think you could give me the case where I would be able to do this, do you? Or even wilder than that. Use the DI register. Think how fancy that would be. And yes, in fact, you can. The name of these addressing modes are called index direct. Says use the contents of SI, add 4 to it, go to that address you just computed relative to the data segment, get 2 bytes of data, plop them into the AX register, doing the appropriate little Indian flip. Can you imagine some of the number of T-states we're going to need to do some of these things? It's going to be phenomenal. But they get it down to very few, actually. The microcode runs very efficiently on the Intel 8088. Okay. Surely you have run out of things you can possibly present to us here. Well, I've got a little comment. One of the comments is, in a base relative situation, either BX or BP, but never both will appear. In an indexed, either SI or DI, but never both will appear. Yeah, but you didn't tell me I couldn't do this. Ha 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 ha, I got you. Well, guess what? It's called base relative indexed mode. Instead of having the index we need out of our array perhaps in hand, we have to compute it. And it's been computed and put into this either the SI or the DI register. So both of these are legit. Oops. So this could be DI. But Mr. Mustaine, you're not telling that I can also do this. They always try to get me, and they always go really hard to get me here. Could I use the BP register and make this business relative to the stack? Would it still be called base relative indexed? And I go, haha, I caught you there. No, it'd be something else. Who wants to tell me what it would be called?
Base relative indexed stack.
You are the man tonight. You are. Let me tell you, you got it. How in the world did you figure that out? You must have programmed one of these machines before. So base relative index stack is a common one, except for we don't often have arrays on the stack, except for high-level languages that actually use the stack to contain local variables. They use something called the heap to contain variables which are dynamically allocated, but they use the stack to contain stuff which is local because it automatically goes away when you go out of scope. And so it's actually fairly efficient. Now, believe it or not, BP plus SI is faster than BP plus DI, and it's the opposite way around for BX plus or something like that. In our world, we'd have to actually look at a T-state diagram to see which was which. But we could potentially do that, and we could figure out which one of these is going to be the fastest instruction, fastest way to do it. Although it's only by one T-state, as I recall. So it's hardly worth the effort. Well, we must have run out of things we can do now. I'll take a couple of breaths here, take a sip of my coffee, being so glad that he said that big long name, base relative index stack for me. I didn't have to do it. Well, I do see one other possible thing. Can anybody see what that might be?
You add an immediate as well.
I think that's exactly what we could look at and see if we might get by with. That would be really a handy thing to have. If I could say something like, move to DL, whatever is BX plus SI plus 1, 2, 3, 4. Of course, I could repeat that with other variants, right? I could say BX plus DI. Or I could say, doesn't have to be DL. Throw an H in there for the heck of it. Wow, that's a pretty powerful instruction. It says I have some place I've remembered in memory stored in this register, so it's probably a variable type of piece of data that happens to have inside of it an array for which I'm operating at this index. And oh, by the way, that array was located 1, 2, 3, 4 bytes into the data segment. So wow. Actually, this is not 1, 2, 3, 4 into the data segment. It's 1, 2, 3, 4 relative to that sum, then inside the data segment. These, of course, are relative to the stack segment. Let's say we took the last one and we wanted it to be relative to the extra segment. What do we change?
Prefix.
All right, we prefix this with what letters?
ES colon.
ES colon, yeah. That says instead of using the stack, which would be your default, use the extra segment, please. Okay, we need a name for this. Oh. Base relative, indexed, direct, stack. No, just direct. I bet that other one is here. Base relative, spell that right in a minute. Index, direct, stack. So that's one heck of a addressing mode there. You know, hey, what'd you use at work today? Well, I was working on the stack for a while, and I used a base relative index direct stack instruction. You are a god. You are purely a god for having used that. I can just imagine you go to a party sometime and you tell somebody you use that. You're either going to think you're the most super geek in the world, or they're going to be impressed. or they're going to think you're an idiot. You always get those people too. So those instructions all are variants of one instruction, the move. Wow. And as a matter of fact, everyone here except for this one are the same type of instruction. And what do I mean by that? I mean they have the same opcode. Whoa, this sounds like this is going to be much more fun than I had ever envisioned, is getting to encode something in one of these particular things. So what we need to do is, first of all, I got something for you to click on the web page. If I can find the web page again. Click on the one that says Datasheet. And we're off to page 27, as I recall. And I'm going to zoom in there, and you can zoom in if you like. At the top left here, actually I can zoom in even more. At the top left are the variants of a move instruction that are possible. Every one we did in the list of things that we had were of this type right here, except for the one that I showed you and highlighted, the one I called immediate. And it is actually one of these two types here. And depending on how you encode it, it might be one or the other. We have specially branded instructions if we're using the accumulator. So if we're using AX or AL, and we're coming from memory or going to memory, these instructions are either slightly smaller or slightly faster. But they all exist up here as well, so we can encode them up here even if they do exist down there. And we have the ones that will go either from a register in memory to a segment register, or from a segment register to a register in memory. Separated out, because remember I told you the segment registers, data segment, extra segment, stack segment, and code segment, require special instructions. So almost everything we wrote is of this class. This is register or memory to or from a register. Notice memory is not on both sides. One of the operands has to be a register. Now in all of these, it could have gone the other direction. Right? I could have taken this last one and I could have moved to wherever BX points plus SI plus 33, whatever is currently in the BX register. So it moves from right to left. That again is base relative index direct. It's not a stack variation. It's because it uses BX and not BP. But it can move either direction, and that's something we have to handily know about, because in encoding it, we have to be crystal clear about what we want the instruction to do. Okay, does anybody have any questions about any of those addressing modes that I put on that page?
With the last one, you're moving data and writing it directly to the memory address?
Yes. The data inside of BX is being put wherever that points in the data segment.
Okay, cool.
This did just the opposite. It went to this address and got memory and put it in the DH register relative to the stack segment. Okay, so I'm going to get rid of him so he doesn't clutter up the picture. And everybody take a sip of water so that you're all ready to start our encoding adventure. On the web page, there is an instruction decode info page. That's this guy. And let me show you how we're going to read this. This is a typical instruction. Other instructions will have similar but different things. If we were actually looking still at this page, well, I guess I got rid of it, but we were still looking at the data sheet, you would have seen on the right-hand side of that, there were little pictures that look a little bit like this. Well, there's specific indications of how that instruction is encoded. But we can use this as a general way of learning all the instructions and then apply it exclusively to the move. So, we go from left to right. However, there can be a byte of data in front of the instruction that changes how the instruction operates. It's normally used for an instruction prefix, like we change the code segment to the extra segment or data segment to the extra segment. That doesn't happen in the instruction. That happens one byte in front of the instruction. We encode a special code there to tell it that the next instruction, when you compute its address, make it relative to a different segment. So we'll forget about that for the moment. Just remember that it is there if we ever need it. The first 6 bytes are the operation code. In the case of our move, they're going to be 1, 0, 0, 0, 1, 0. Next, we have a bit called the direction bit. We go down here and look at the table. Direction bit says we're going to encode it as a 0 if the instruction source is specified in the register field. Ooh, that sounds scary. And a 1 if the instruction's destination is specified in the register field. Okay, just briefly thinking about that for a second. In all of these instructions, even the ones that point the other direction, one of the operands is a register. In the case where it's on the right-hand side, that's the source. Data comes from here to there. In the case of where it's on the left, it goes from here to there. It would be the destination. So this D bit would be coded as a 0 in this instruction because we're going from the register to the memory. And in this particular one, we're going from here to there. So it's the destination, so we would code a 1 in the D bit. Where that's cloudy, well, I don't even have them on this page, was, yes, I do. Which one is the destination, which one is the source? Remember earlier I told you there's 2 ways to encode these instructions? We can code it once, pretending like that's the source, and we can encode it the other way, pretending like that's the source. But it doesn't matter whether it's the source or destination. What matters is it encoded in the instruction in the field called REG, which is normally reserved for the register, which of course is confusing when you have 2 registers. Let's go back and continue. The next bit tells us whether we're working with a word or a byte. 0 if we're working on 8 bits, 1 if we're working on 16-bit data. So that'll be an easy one for us to figure out. If we're using AX, we code a 1 because it's 16 bits. If we're using DL, we code a 0 because it's 8 bits. And this applies to the amount of data being moved. Now we have something called the mod flags. It's 2 bits, and mod is really mode. And it's really going to tell us which register or memory mode we're operating in, and if there's a displacement with that mode, how long is it? And you go, but I only have 2 bits. Well, that's okay. We'll deal with it in the table down at the bottom here. So, if the mode field is 0, 0, it says we're operating in memory mode only. It means there is no direct offset encoded anywhere in the instruction, except, if you read the note, when it's a 1, 1, 0 for the what's called the RM, we haven't looked at yet, then only a displacement follows. There are no other registers specified. So there's one special case. If we code a 0, 1, it means we're going to be in 8-bit mode with a displacement. 10 means we're in 16-bit mode with a displacement. 11 means we're in register mode and there is no displacement at all. So we'll come back to these in a minute. The next 3 bits tell us what register is going to be either the destination or the source as specified back here in the D bit. So if we say it's the destination, we put a register here, that's going to be the register will be on the left-hand side of the comma. We say it's a source, we put a register here, it's going to be on the right-hand side of the comma because it's coming from the register. But the actual register value gets stored here, which register it is. We go down and look at this table. Register 000, if we're operating on 8-bit data, means it's the AL register. If it's 001, it's the CL register, and so forth. 111 would be the BH register. However, if we're working with 16-bit data, 000 means the AX register. 010 means the DX register. 101 means the BP register. 111 means DI. So these registers can mean various things about the registers. I also listed the segment registers if you ever needed them, but we don't use them in this exercise. Then we have 3 bits, which are used to indicate whether or not we have another register, meaning the second register, the one that was not the source or destination over here, and those that use 2 registers. And if not a register, which one of the mode kind of divisions are being used. Remember, we have to a displacement, but we don't know how long it is. So if we go down to this other table, if the mode is 11, then we know that RM is going to contain a register. Which register? Well, it's the second register. It's the one that's not the source or destination we specified in the reg field. Otherwise, it's going to be either a 00, 01, or 10, in which case this RM field is going to say, is it base relative indexed? Is it base relative indexed? Is it base relative index stack? Is it base relative index stack? Is it indexed? Indexed? Is it direct? Is it base relative? Or is it base relative indexed with an 8-bit displacement? So base relative index direct. Both of these are, but one has an 8-bit displacement, the other has a 16-bit displacement. We want to code it in as short of a coded field as we possibly can without causing a problem with the sign bit. We never want to code an 8-bit entity with a 1 on the left-hand side. We want to force it to be 16 bits so we can include in that extra byte extra 1s or 0s to indicate that this was either positive or negative. So we got plenty of data here, and you've got this sheet in front of you. So it shouldn't be too much trouble to actually encode an instruction. You're going, this teacher's crazy. This is going to be a pain. Well, not really. Let me pop this up to the top of the screen. Let's list out here what we're going to need to have. We're going to need to have a 6-byte opcode. We know it's that, so I'm just going to leave it alone. What was next? The direction flag? And the word flag? And the register? Oh, I guess the mod is next. And it's only 2 bytes, so I'm going to abbreviate it as MD. And the register, or the R/M. And then any displacement would follow. So let's take an instruction, and using that template up there, let's encode it. Let's move to AX whatever BX points at. So this is what's the addressing mode of this particular instruction? I know somebody's going to ask you that. Somebody pop up a mic there and tell me real quick. What's the addressing mode of that instruction?
Is it base relative addressing?
Yes, it is. Very good. Okay, so let's encode it. Let's go up here and do our encoding. We know the opcode is going to be the same. Is AX the destination or the source?
It's the destination.
It's going into AX, so it's the destination, so we code a 1. Are we moving 1 bit of data or 2 bytes? Two bytes of data or 1 byte of data?
2 bytes.
2 bytes, so we code a 1 for a word. Now, what mode are we using? We have to look at the mode table. And the mode we're operating on, let's see, which page is this at this guy? The mode we're operating in is going to not have a displacement because we don't have any offsets inside the parentheses. They're not both registers, so it's not going to be this guy. So it's going to be a 0, 0. Now, what register did we use? We used AX. So we look at our table of registers. AX, when word is a 1, is coded 0, 0, 0. Now we have to go to the mode table, find which line just has BX on it. Down here at the bottom, under 0, 0, it's a 1, 1, 1. Okay, so let's grab those bytes. I'm going to stick them down here for the moment. I'm going to collapse out the spaces. And then I'm going to divvy it up into nibbles. I'm going to write down the hex. 8B07. So the instruction 8B07, if you found it in memory, could be reversed into this, and we would know what the instruction looked like because that's the instruction that we've just created. 8B07 has to be that. So given this, we can get to the hex value, of course, but given the hex, we can get to this, which could get us back to this. Or we could start with this and get to the hex. We can move fluidly among all of those encodings. But this is what we would see in memory if we had this instruction. Ready to do another one, or do you have a question about that one? Okay, let me give you one here. Encode that instruction. I'll be cleaning mine up as we wait. Use your sheet. Anybody have an answer yet? Give me a green light if you have an answer. Okay, no answers yet. Okay. Anybody run into trouble? Okay, well, the problem is the only registers that can be inside those brackets are BX, BP, DI, and SI. So you're not going to find that anywhere. You can't encode that instruction. It would be a compiler or assembler error. So let's modify it. Let's say we wanted to do BH from AH instead in here, so we'll use BP, I'm on the wrong keys again, BP. Now this one is encodable. This says go to wherever BP points on the stack, take 1 byte of data and put it into the BH register. So let's encode that one. I'll give you a couple seconds so those of you that are way ahead of the rest of the class can get them done, and then I'll jump in and help everybody else. What's the addressing mode of this one?
Base relative stack addressing.
That's correct. Okay, so let's move along here together in case some of you are stuck. We're going to be moving which direction? Is the register the source or the destination in this one? What's the destination? We moving 16 bits or 8 bits? 8 bits. Is there any displacement? Well, we saw the chart a while ago. The only ones that have displacement are 01 and 10 because 11 was both registers, so we have to be in mode 00. The register is the BH register. Come over here to BH, 111. And then finally we need to go down to the mode table and find the one that has BP all by itself in parentheses. Anybody see it? And the problem is there is none that is just base relative stack. Even though that's a legal addressing mode, base relative stack, there is no just BP all by itself. So what we have to do instead is we have to encode it as BP plus some zeros. A reasonable one is to change our mode to 01. Grab the line that had that in the table here, which is 110. And then we're going to put 8 zeros, which are the 8-bit displacement that follows the instruction. So let me grab that. Encode that into hexadecimal. And that would be the instruction that matches this guy. So it's the same as if we had put in here plus 0. It's just one of the little things they did in the, because they had to support the direct address as a single line, they had to get rid of one of the lines. The line they got rid of is the least used one, which would be just relative to the base pointer without an offset, because you can always code a 0. And the assemblers know to do that for you. So if you were writing an assembler, which is one of the reasons you learn to do this, you would take care of that for the programmer, and he wouldn't have to write the 0. He wouldn't have to know about it. Okay, you guys getting the swing of this? Let's do another one. Let's do a hard one. What do you think? That sound like a good idea? I say that, then I give you an easy one, and you all are so disappointed. Let's move to dx plus di plus 234, which is in hex, from, I don't know, let's go CH. First of all, what is the addressing mode of this instruction?
Is it base relative index direct?
You got it. I think if I'm going to cheat on this test, I'm cheating off of you this time. Actually, I did not say we caught some people that I haven't told them yet, but they unfortunately got a hold of some of either the summer answers or last semester's. I won't even tell you the story right now, but we know more about them than they do. This says take what's in CH and put it wherever this points in the data segment. So let's encode this. What is the register direction? Is it a source or a destination in this one? Somebody get on the mic and tell me.
Source.
It's the source.
Okay, we're moving 8 bits or 16 bits?
8.
Do we have a displacement? What's our mode? Well, first of all, can it be stored in 8 bits? 2, 3, 4. Nope. So it's going to have to be 1, 0. Right? Because it says we got to have a 16-bit displacement if it's 1, 0. Then what goes in the register field? Well, which register am I going to encode? BX, DI, or CH? Come on, you know the answer to that.
CH?
Yep, you bet. What is the code for CH?
0.
What is it?
0.
They need 3 numbers. 101? Is that what somebody said?
Not the wrong thing. 101, yeah.
Okay. And since we're in the mode table now, we're looking for BXDI displacement. Mode over here. BXDI displacement. Which line is that?
Second.
Second line, which is code 001. Now, we're not done yet. We have to code the 2, 3, 4, but be careful. We have to code the 3, 4, 0, 2. Okay? Little Indian. This is really 0, 2, 3, 4. This will get stored first in memory before that. So let's copy that guy down and break him into little things. Anyway, you all do know that getting a hold of a copy of last year's test or the summer's test is cheating, right? And that's the same as talking to somebody or communicating with somebody about the test. So stay away from that. Okay, so there's our thing. Write that down just as a hex practice. See how fast you can write down those hex digits. See if you can do it so fast that your other hand didn't even know you were writing. I will sluggishly start typing them in here, probably on the wrong keys. But that's the instruction that's encoded down here. If we found this in memory and we're the executing thing, if the IP ever points at this and it's in the code segment, we're going to execute that instruction. We're going to get the 1 byte that's in CH put at wherever BX plus DI plus 2, 3, 4 point. And so you can even visually here see the 2, 3, 4 in the instruction. Okay, I have to look one thing up real quick. Let me see if I can find it quickly. I have to do it on this screen over here because it's the only one that's got this program on it. Let me try to download that. I'm going to type the URL here, and later if I get it right, I'll have you type it as well. You might want to get started typing it, just if I can read my handwriting over there. 8088 underscore capital INST underscore matrix.pdf. Let me see if that's it. Forgot all about this file. That's it. Okay. Let me put that URL back up so you can get a copy of it. Give me a green light when you've got a copy. Ooh, I gotta get another window up here. I'm not looking at the right place. There we go. Oh, look at you guys. You guys are fast as I am sometimes, and I'm really fast. Don't usually type the right words. Okay, that's almost everybody. Okay, so once we have that, let's take a little tour about what it says on it. I'm going to zoom mine up a little. Let me see if this will do it for me. Across the top and down the side are the first part of an instruction. So if you were to just take the first byte, remember we're only using 6 bits, but those other 2 bits could be decoded to say that when they're this is the instruction you're executing. And we can go in this table to any particular intersection, and we can find an instruction that we were interested in. So we've been doing moves. What was the last one we just did? Let's see, where is it? Did I save it? Was this it? Yeah. 8, 8. So if I go to the intersection of 8 and 8, I'll find there's a move instruction. The move instruction is of the type byte with a from field set rather than a transmit field. It's hard to see the character. And then the RM field as opposed to it being just a register. So it could be register or memory. So I could use this to double check that I did the right thing. But more importantly, I want to point out to you that at location 2, 6, we have what's called the segment override for the extra segment, 2, 6. At the next row down, 3E, we have, if we wanted to override something to the data segment. We normally wouldn't use the code segment or the stack segment, but this one comes quite handy. So in our last instruction, what was that, number 26? If we had, instead of writing it this way, we had said, by the way, we're not relative to the data segment, we're relative to the extra segment this time. In front of all of this, there would have been a 2, 6. So this now becomes that instruction. Same addressing mode, is still base relative index direct. We just happen to be using the extra segment as the target rather than the direct, or the data segment. So be careful of that, because if somebody asks you what this instruction was, you go to 2, 6, you're not going to find a move. You got to know that thing means there's a segment prefix and that the next byte tells you what the instruction really is. It's a move instruction. So let's do another one here. We'll do one for confidence and one that's hard. No, let's not do it that way. Let's actually, let's do this. Do this one for confidence. First of all, what's the addressing mode of this?
Base relative index direct stack addressing.
That's correct. These are out of order. Some assemblers would care. Most of them don't care. Does it matter that I have both SI and DI in the same instruction? The answer is no. They just can't both of them be inside the brackets. So you can have one SI, one DI, one BX, one BP, but you can't have two BX. You can't have a BX and a BP, and you can't have an SI and a DI. Or you can just have none. Minus sign simply means this number is coded as a 2's complement number. So that's not a big deal. But you got that exactly right. It's base relative index direct. Because we're in the stack segment, it's stack. So is the register the destination or the source?
It's the destination.
Destination.
Yeah, destination. We're moving 8 bits or 16 bits. Don't be afraid. If you talk on top of somebody, that's just fine.
It's 8 bits.
Is the DI register 8 bits or 16 bits long?
No, 16 actually.
Okay, 16. Now, mode. If we're all registers, meaning registers on both sides, this will be 1, 1. If we have no displacement, it's 0, 0. We have a displacement. Can the displacement be critically shown in a single byte to be a -2? Or does it take 2 bytes to show that it's a -2? Well, what is -2 in 2's complement? Just write it up here so we have it written in binary, first of all. That's a 2, right? Flip all the bits and add 1, or as Coakley method says, do that. So FE is equal to -2. So this is the same as if we had written plus FE, assuming that these values are in X. At this point, because it's going to get automatically sign extended to 16 bits, it's clear to us and anybody maintaining this, we mean -2. If we coded it this way, we wouldn't be wrong. We just eat 1 more byte of memory. So the better choice is probably either to be clear like this, or if you're working with people you know, to do this. But that tells us it's an FE, which is what the programmer's intent was, to indicate to us it's -2. It's easier to read than looking at FE and trying to figure out if that's a -2. I even wrote it wrong here. That's a -2. No wonder. So the mode we're in says we can put this thing into 8 bits. Which mode is 8 bits? We know it's not 0, 0, and it's not 1, 1.
0, 1.
0, 1. What register we're using? DI, what's its code?
Is it 111?
111? That doesn't sound right. I thought BI was 111. I trust you. Okay, so in the table here, we need BP plus SI plus a number. So let me see if I can find my table again. I've lost it here on the screen somewhere. That's not it. Where did I have that? This page? Yeah. So BP plus, what was it, DI plus 8 bits? Was this guy?
Yep.
And he is a 0, 1, 1. Are we done?
Wait, aren't we using SI, not DI?
Oh, yeah, we are. So SI was the guy above him, which is 010. So now we still have to encode the -2. So we need, because we said it's in 8 bits, we can encode 11111110. Grabbing that, putting it down here and get rid of the spaces. And then put it back into sets of 4s. We will see the number 8, B, 7, A, F, E. You get that right? Yes, check me. Okay. Now that we're getting really good at these, let's move AX from BX. Do that one on your own, or you can use chat there to talk to somebody else if you're lost completely. Let's hope you're not lost. Give me a green light when you get the answer. Okay, a bunch of you are starting to get it. Now this is the one we talked about is going to have 2 solutions. So I'll separate the solutions down there so we can do them at the same time. First of all, we have to decide whether we're going to encode AX in the register field or we're going to encode BX in the register field. We can do it either way. Let's on the top line, we'll put AX in the register field. And when we do it the second time, we'll put BX in the register field. So if AX is in the register field, is it the source or destination?
AX is the destination.
It's a destination, okay. We're doing 1 byte. Oh, I'm sorry, 2 bytes because it's AX and BX. The mode is register to register, which is 1-1. That's the mode you see right there. No displacement. Now we need to code the AX register. I'm not looking at it. What's the value for AX? Is it 000?
Yeah. Yeah.
Yeah.
Then we have to encode BX in the other part. What is BX?
011.
Okay. There's the encoding. Let's do the other one. If BX is in the register field, is it the source or the destination?
It's the source.
Source.
Okay, still 16 bits. Same mode. We have to reverse the encoding. Right? Same 2 registers, we just have to reverse where they're encoded. So one of the encodings for that instruction going to look like this. The other one is going to look like this. You write down what those are. 8B Charlie 3. 8-9 Dog 8. Now, who'd have thunk it? That and that do identical things on this machine. So being presented with one of those, if you determine it's a register to register, make sure you do it thoroughly to make sure that you're not looking at the other one, you know. So make sure that if somebody asks you about the register one, you do both, because both are legitimate instructions. That only happens on the register to register instructions. Anybody have any other questions about this encoding? We're not going to do anything else with the 8088, even though it's the, one of choice on PCs. Like I say, if you ever have a job where you need to do it, you'll learn it then, I guarantee you. But this background will be excellent for you to have in any other assembler you use as well, to be able to decode and encode things like instructions and be able to recognize them in memory. Anybody have any questions?
I had an oddball one.
Okay.
This goes back to the registers themselves. Is there some physical hardware difference that makes like the SI, DI better suited to being indices, or SPPP better suited to being pointers? Or
They are hooked up to the, we're looking at the, which I don't have open here. I actually gave you a link to it. I think we opened it once. The data sheet. If we were to look at the actual physical bus pictures, what you'll notice is these are all part of the execution unit. They're all attached to the A bus in the same sort of way. They, however, are used through this summing unit up here by passing through the bus. This double line here is a little thing. So the bus interface unit knows how to do arithmetic on these when it's doing address arithmetic faster than if you're just using it to contain data. These guys are lightning fast for data, but would be terrible for addresses, except for BHBL, which has been optimized as part of the memory interface. This is too complicated to explain the details like pipelining and all that stuff. But basically, we're looking at a very similar thing to what we saw for the SAP1. It's not really that different. Just follow the arrows. In this case, there's at least 3 buses, because I see a C bus and an A bus. Here's the B bus over here. Any other questions? Okay, Monday is the exam. You know what it's going to cover. If for some reason we can't get on Blackboard, it will be, explicit instructions will be posted on the website on how to take the exam. There is to be no cheating on the exam. Okay, and you know what that means. Don't try to find some outside case where you believe it would be okay. If it smells like cheating, it's cheating. And I wouldn't be saying anything except we had a couple people dabble in that in the last exam, and they unfortunately set off some traps. But, well, who knows? Some other people might have also not set any traps up, but if you did, shame on you. So hopefully I'll see you at 6 on Monday. We'll try to do, well, I guess I want to give you as much time as possible to get the exam done. The test itself, the main part of it, the question part, should be fairly quick and fairly easy. I'm going to encourage your grades to go up a little bit. But there is a do it part of the test. And the do it part of the test is relatively easy if you've been paying attention, but if you haven't been paying attention, it could give you some pause. So make sure you're thoroughly studied up before you get here, and you know the stuff to study. Buses, FPGAs, the HDL stuff, which one do we use? VHDL, anything having to, and no more than we did on it. I mean, we're not looking for deep hidden secrets that are hidden away in a book somewhere, just kind of at the level we had talked about it. And then anything having to do with the SAP 3, 2, or 1, the 8085 only to mention it as being similar to the SAP 3, and then be able to do these addresses and look at instructions and figure out, what they are. Or, to encode one if you had to. Anybody have any question about that? Okay, well, I see a jar of jelly in the kitchen, so I think I'm going to go in the kitchen and get myself some jelly. And I will talk to, or see you guys on Monday at 6 o'clock. Make sure you're here and on time.
Thank you. Good night.
Bye-bye.